Hello everyone, I am Omit Roy and today I will present my work Graph Anomaly Detection via Neighborhood Reconstruction termed as GAD-NR. And the co-authors of this work are Joan Shu, Jia Lee, Carl Young, Oliver Elshoft, Jaron Smits, and Professor Penley. This work is accepted as a conference paper at the 17th ACM International Conference on Web Search and Data Mining 2024, happening on March 4th to 8th, 2024 at Yucatan, Merida, Mexico. So first I will describe the problem definition, that is what is graph anomaly detection, and I will describe several types of anomaly that is observed in the literature, and then I will describe some of the state-of-the-art node anomaly detection and their limitations. Then I will describe my work graph anomaly detection via neighborhood reconstruction, the two parts, that is encoder and the decoder, and in the decoder part I will describe the self and neighborhood reconstruction and how we combine them to detect anomalies. And in the experimental results section I will describe the several type of anomalies that are injected in the benchmark data sets. Then I will describe the performance of GAD-NR on the benchmark anomaly detection, on different type of anomaly detection like contextual, structural, or joint type, and some running time analysis with state-of-the-art approaches. And also I will describe some future directions of this current work, GAD-NR, and some references. So first, let me define the problem graph anomaly detection. So given a graph G, it can be represented by a adjacency matrix A n by n and feature matrix X, and where each node will have an anomaly level 0 or 1. And this problem of graph anomaly detection or node anomaly detection is different from node level classification because anomalies are those entities that have low li low likelihood to be appeared in a particular distribution. And in this work, we aim to detect anomalies or anomalous nodes via learning the distribution of each node via neighborhood reconstruction. And by neighborhood of a node, we represent its features, the degree of this target node, and the neighbor features. So let's first look at some types of anomaly. So there could be contextual anomaly where one node will have significantly different features compared to other nodes in the network. So it could be like spammers or fake account holders in a social media network who doesn't actually uh, add information in their profiles. So their profiles or their features in a network is quite different compared to other normal nodes. Then there could be also structural anomaly, where as a group of nodes are densely connected with each other. It could be some malicious sellers who are exchanging fake reviews. So there will be super dense connections between them. And then also it could be joint type anomaly, where a large number of phishing emails is sent to users in an email network. So you can see that a particular node is connected to almost all nodes in the network, and it has also the features which is quite different. So here are some state-of-the-art node anomaly detection approaches. There could be structure-based approaches like using graph features like centrality measure or clustering coefficient to detect anomalies, or network clustering approaches. Then also there could be feature-based approaches like k-nearest neighbors, some node embeddings, or using multi-layer perceptron to detect anomalies. Also, there could be deep learning based approaches, say graph autoencoder based approach, say GCN autoencoder dominant anomaly DE. But the problem of deep learning approaches or graph autoencoder based approaches is they use link prediction loss, which is not quite suited for the graph anomaly detection task that aims at learning the distribution. Rather, it is more suited for link prediction because they bring similar nodes closer to nodes with similar features closer together in the latent space. Also, there could be contrastive learning based approach and self-supervised learning based approaches. We can view that according to the state-of-the-art anomaly detection approaches, the structure-based methods can detect well structural anomalies, but they fail to detect contextual or joint type anomaly very well. And also, feature-based approach is more suited for the contextual anomaly, as the contextual anomalies are feature-wise different from other nodes. Also, graph autoencoders with proximity-driven loss can detect both contextual and structural anomaly, but they fail at detecting joint type anomalies, which uh, needs the neighborhood reconstruction idea or neighborhood reconstruction based which needs to consider the neighborhood rather than the link prediction type loss. So we made some assumptions here. It is well. So the normal nodes neighborhood are contains more information or more relevant information. So it could be more easily reconstructed compared to anomalous nodes. Also, uh, learning the distribution of each node via the neighborhood reconstruction can decide whether the node lie in low probability region or not, and we can use it to detect anomalies. Um, so the motivation is general graph encoders only use linkage information to reconstruct the links, and it is not very well for the graph anomaly detection. Also, some local structures, neighbor features are ignored, which is essential for learning the underlying distribution, which is important for the graph anomaly detection task. Considering all this, we designed our approach, GAD-NR, Graph Anomaly Detection via Neighborhood Reconstruction. And our approach consists two different parts, encoder and the decoder. In the encoder part, we consider the one hop neighborhood or multi-hop neighborhood of a target node U, and use some graph neural network like GCN or graph sage to encode the neighborhood of a particular node U to obtain its latent representation HU1. After that, this one means the we are using one hop information or one layer in the GNN. After that, we are trying to use this HU1 or the latent representation of node U to reconstruct its degree, its self feature, and also its neighborhood. So in the neighborhood, we define it as a say if the node U has D neighbors, then we will have D neighborhood features. But the number of neighbors can vary from one node to another. So if we try to exactly match the neighborhood features, then it will be like it will be time consuming for the model to reconstruct different number of neighbors for different features. So for this, we first calculate the mean and variance of the neighbor features, and we try to predict that mean and variance. Since a Gaussian distribution can be represented using the mean and variance, so our goal is to minimize the KL divergence between the target distribution and the predicted distribution. And by minimizing the KL divergence between the target Gaussian distribution of the neighbors and the predicted Gaussian distribution of the neighbors, we are trying to match the neighborhood here. So here are different parts of the GAD-NR. It is the encoder is a GCN or GIN, which can encode one or two of neighborhood. And in the decoder, we are decoding the degree, the self feature, and the neighbor feature distribution by minimizing the KL divergence between the target Gaussian neighborhood distribution and the predicted Gaussian neighborhood distribution. And there are some regularization. There are some hyperparameters like lambda x, lambda d, lambda n to vary the impact of different type of reconstruction loss in the loss function. And we combine all of these terms to and use that combined loss as the outlier score of a target node U to detect whether the to determine whether the node U is anomaly or not. Then we describe some benchmark anomaly detection data sets here. We use the benchmarking outlier node detection paper from NeurIPS 22 and include several and follow their setting to inject different type of anomalies like contextual anomaly or joint or structural anomaly in the benchmark data sets. And we also include the anomaly ratio here. And in table 2, we present the performance of GAD-NR on benchmark anomaly detection. For the 5 datasets, we Reddit, Disney, Books, and Android, we use the benchmark anomaly level. But for Cora dataset, the anomaly is injected, and we followed the same setting as the bound paper. And we use this following values of the lambda x, lambda d, and lambda n, the hyperparameters for which denotes the impact of self-feature reconstruction, degree reconstruction, and neighborhood reconstruction, we can view that GAD-NR can outperform uh, the baseline anomaly detection or graph anomaly detection models in 5 out of the 6 data sets, and which shows that our neighborhood reconstruction approach is very much like impactful in detecting anomaly nodes in these data sets. Also, we present a direct performance comparison with neighborhood assistant reconstruction based graph autoencoder, where they try to use Western distance or Hungarian laws to match the neighborhood other than the tail divergence that we are using here. So we can see that our method GAD-NR can outperform NW at JE both in performance and in running time. And in the running time, we can view that the improvement is very much notable. And then we present the performance of GAD-NR in contextual and structure type, that is structural and joint type anomaly detection. And we can view that GAD-NR can perform well in almost 4 data sets in contextual anomaly detection. And almost all dataset in contextual anomaly detection. And we can view that without the feature reconstruction part, the performance of GAD-NR drops. And the reason is without the feature reconstruction, the contextual anomaly, which is feature-wise different from the other nodes, cannot be detected. And also we can view that without the without the neighborhood reconstruction part, the structure type, it is structural and joint type anomaly detection performance is dropped. So we can view the impact of different type of reconstruction laws in detecting contextual and structure type anomaly. And we also present the joint type anomaly detection separately, and we can view the same pattern here. That is, when the neighborhood reconstruction loss is removed, then the performance of GAD-NR drops in joint type anomaly detection. Next, we present the impact of different type of reconstruction loss on Cora and Books dataset using these plots, and we can view that this blue curve, which represents the contextual anomaly detection, the performance improves when the impact of on the reconstruction of feature is added, and also the uh, orange curve here, which represents the structural anomaly detection. The performance also increases when we increase the impact of neighborhood reconstruction, and but the impact of degree reconstruction is more or less neutral in both data sets in different type of anomaly detection. The future direction of this work is to apply neighborhood reconstruction for dynamic graph, and to define how dynamic neighborhood reconstruction can be defined in dynamic settings or dynamic graph anomaly detection setting. And here are some references that we have used in our presentation and in our work. So here my presentation of GAD-NR concludes. Thank you, everyone.